Hello, dear participants of the conference. Today I would like to present work fiber optic system for monitoring coolant parameters in nuclear power plants. Currently, in conditions of many various kinds of interference, for example, electromagnetic vibration, there are problems with transmitting information, especially under challenging conditions. These problems are solved in various ways. The most promising of them is using a fiber optic transmission system. But a difficult situation arises in nuclear power plants when it is necessary to measure the coolant's current flow parameters inside the reactor's protective zone. The efficiency of electricity production and the safety of a nuclear power plant depend on the optimal choice of these parameters. Molten lithium or lead with nickel, sodium, or water salt solution at different temperatures are used as a head carrier. High temperature and chemical activity and many interferences create a lot of problems with the use of various meters, even with the use of fiber optic communication lines for information transmission. The error in measuring various parameters increases, which complicates the control of the reactor operation. Therefore, the development of new systems for measuring the coolant parameters with a small, about error of 1% is very important. One of the possible options for solving this problem is the fiber optic system developed by us. So, one of the operation features in nuclear reactors is the presence of oxygen activity in the coolant. Oxygen activity is present only when the reactors operating at high energy levels of power and decreases almost immediately after the termination of chain reaction. When a coolant with oxygen activity flows through the pipeline, additional gamma quanta are emitted due to decay of 16N knuckle. An addition is made to the natural background of radiation present in this zone. These are additive to the exposure dose of radiation acting on the optical fiber is of pulse nature. It appears in a certain zone of the pipeline due to the uneven distribution of neutrons with the energy of more than 9 MeV in the coolant, which, when interacting with the oxygen nuclei, that make up the coolant from 16N nuclei because of the reaction. The appearance of these gamma quanta in the area of the optical fibers coils sharply increases the number of its centers. Radiation-induced losses increase, which is determined by the following formula on the slide. So here, the structural diagram of the fiber optic measuring system. The POUT value recorded on photodetectors 15 and 16 and its decrease. Supposed coils with optical fiber are located on the pipeline with a distance L between them and the coolant's flow separated by protective screens. In that case, decreasing the value of Pout in the second coil will begin after some time, delta t, which corresponds to the flow of this segment of the coolant from the first coil to second through the pipeline. Having established the same cutoff value for Pout, provided that two coils receive laser radiation from one source with the same power, it is possible to determine delta t using comparison circuits. The value of the flow rate of the Coulomb Q is determined by the following relationship. And after measuring delta T using the previously developed method for controlling the relaxation rate of its centers in optical fiber, alpha S is restored to its initial value, and the process of measuring Q can be carried out again. Also, another critical parameter of the coolant is the level of oxygen activity. It also needs to be measured. The previously developed ionization chambers for measuring the flux of gamma quanta in the zone will work with significant failures, and there will be a problem with the transfer of information. Our studies of the effect of gamma radiation on the formation centers in optical fiber allowed us to establish that a certain laser power being where an equilibrium can be established between two processes, the formation of new and relaxation of existing E-centers. In this case, the recorded power of laser radiation at the output remains unchanged. So the following relationship is fulfilled. Next, we introduce the power of gamma quanta, which was spent on forming n new E-centers in the optical fiber. So in this case, the value E can be calculated also by this formula, and then we can find the value of n using the following relationship. In this relationship, the values of the laser power P in and P out are matched. The value of sigma is established experimentally for each type of fiber, since it will depend on the percentages of doping of the core of fiber with the germanium oxide and the temperature of the fiber. Therefore, when conducting studies of oxygen activity of the coolant, it is necessary to control two temperatures, the coolant and the fiber, and its flow rate Q. So the results. These figures show the results. The first one shows the results of changes in the power of laser radiation and the output of optical fiber from time t when exposed to gamma radiation in the form of a pulse with a duration of 2 seconds, and exposure dose is 100 gray for various types of the optical fiber. On the right picture, as an example, the process of controlling the relaxation in E-centers in an optical fiber after the termination of gamma radiation, while maintaining their radioactive background, is presented. The results show that the fiber with a pure quartz core is less sensitive to gamma radiation. With an increase in the degree of doping of the optical fiber core, the loss of alpha S and the stiffness of their rise increase. Therefore, the system developed by us uses fibers with a high degree of doping of germanium oxide. Next, these two figures show the dependencies of change in voltage at the outputs of two photodetectors on the time. According to the presented changes, using key sockets, the value of the coolant flow rate Q is determined. Further, by measuring the values of P in and P out, we determine N. The results obtained are presented in the following form. For example, for a reactor with a water salt solution of the coolant at temperature of 896 kelvins, the value Q is about 126 and it is about 109 for 1 second. Such data, if necessary, are presented in our paper. The obtained results show that the fiber optic system developed by us makes it possible to measure the coolant parameters. So it's the flow rate Q and the level of oxygen activity N. It makes possible to control the reactor's operation in optimal heat exchange between the coolant and feed water in the second loop. And by adjusting the coolant parameters, it is possible to ensure the best mode of operation of the steam generator at nuclear power plant. So it will reduce the losses in electricity generation and increase the service life of the equipment. Thank you for your attention.